Welcome back to our lecture series on structural characterization of materials. I am Professor Ashutosh Tiwari from the Department of Material Science and Engineering at the University of Utah. In the previous lecture, we focused on how resolution and image quality in SEM are determined by where signals originate, the size of the interaction volume, and operating conditions such as accelerating voltage and probe geometry. In this lecture, we take the next step and ask a more practical question: where do these beam conditions actually come from? Parameters like probe size, probe current, convergence angle, and accelerating voltage are not abstract things. They are ultimately controlled by the hardware of the microscope. To understand how these parameters are established, we begin with the most fundamental component of the SEM, the electron source. The electron gun determines the brightness, stability, and energy spread of the beam, and it sets the fundamental limits on what the microscope can achieve downstream. This lecture focuses on how electrons are generated, the physical mechanism behind different types of electron sources, and why the choice of source matters for imaging performance. At the system level, a scanning electron microscope is built from a sequence of components that work together to form and control the electron beam and produce an image. At the top of the column is the electron source, which generates the primary beam. Its properties such as brightness, stability, and energy spread set fundamental limits on resolution and signal quality. This beam is then shaped by electron lenses into a fine probe at the specimen, while the scan system controls how that probe is rastered across the surface, defining magnification. As the beam interacts with the specimen, various signals are generated and collected by different detectors, and these signals are converted into an image by the computer. This system-level view provides context for the rest of the course. In this lecture, we focus on the first and the most critical element, the electron source, and how it determines the beam conditions used in SEM. Every SEM image ultimately traces back to the quality of the electron beam, and that quality is established at the electron source. The electron gun is responsible for generating the primary electrons that will later be focused, scanned, and detected. The key beam property such as brightness, temporal stability, and energy spread are all defined at this stage. Brightness determines how much current can be delivered into a small probe, which directly affects resolution and signal-to-noise ratio. Stability controls how steady the beam remains over time, influencing image drift and noise. Energy spread affects how uniformly the electrons respond to the focusing lenses and influences chromatic aberrations in the column. While lenses and operating conditions can shape and refine the beam, they cannot compensate for fundamental limitations imposed by the source itself. For this reason, the electron gun sets the upper performance limit of the SEM and plays a central role in determining what level of resolution and image quality is achievable. In SEM, the primary electron beam can be generated through two fundamentally different emission mechanisms, and this distinction has important consequences for beam quality. The first category is thermionic emission, where electrons are released from a material by thermal excitation. Heating provides electrons with enough energy to overcome the surface potential barrier and enter the vacuum. This approach is technologically simple and robust, but it typically produces a beam with lower brightness and a broader energy spread. The second category is field emission, where electrons are extracted from the surface by an intense electric field applied at a very sharp emitter tip. In this case, electrons tunnel through the surface barrier rather than overcoming it thermally. Field emission sources generate beams with significantly higher brightness, improved coherence, and a narrower energy distribution. At this point, the important takeaway is conceptual rather than mathematical. The mechanism of electron emission directly determines beam brightness, stability, and energy spread, and therefore sets the ultimate performance limits of the SEM. In the following slides, we will examine these emitter types individually and connect their emission characteristics to practical imaging performance. Thermionic emission is one of the most widely used methods for generating electrons in an SEM and is based on a straightforward physical process. In a thermionic process, electrons are released from a material by heating it. As the temperature increases, electrons gain thermal energy. When this energy becomes sufficient to overcome the work function, the surface energy barrier that binds electrons to the material, they can escape into the vacuum. The emission current increases rapidly with temperature, allowing the beam current to be controlled through the heating power supplied to the emitter. This mechanism is employed in commonly used SEM sources such as tungsten filaments and lanthanum hexaboride LaB6 emitters. Because emission is driven by thermal energy, thermionic sources are generally robust and stable, but the emitted electrons exhibit a broader energy distribution and lower brightness compared to field emission sources. The physical picture to retain here is that thermal excitation enables electrons to overcome the surface potential barrier, and the efficiency of emission is strongly influenced by the material's work function. In the next slide, we will examine specific thermionic emitters and see how differences in material properties translate into differences in SEM performance. To understand thermionic emission, we need to look closely at what happens at the metal vacuum interface. Inside a metal, electrons occupy energy states up to the Fermi level, labeled here as EF. Even though electrons are free to move within the metal, they cannot leave the surface easily. At the interface with vacuum, they encounter an energy barrier known as the work function, shown here as EW. This work function represents the minimum energy an electron must have to escape from the metal into vacuum. Simply, being at the Fermi level is not enough. The electron must acquire additional thermal energy to overcome this barrier. When the metal is heated, some electrons gain sufficient kinetic energy. These are the so-called hot electrons. If their total energy exceeds the work function, they can cross the barrier and escape into the vacuum, becoming part of the electron beam. This diagram highlights an important point. Thermionic emission is fundamentally an energy barrier problem. The highest the work function, the harder it is for electrons to escape, and the higher the temperature required to generate usable emission. This is why materials with lower work functions are preferred for electron sources. They allow emission at lower temperatures, improving efficiency and a filament lifetime. The behavior of thermionic emission can be summarized by the Richardson equation. The equation highlights two important dependencies. First, the emission current density increases with temperature. As the emitter is heated, more electrons acquire sufficient energy to escape the surface, leading to a higher beam current. Second, the emission current depends exponentially on the work function. This exponential dependence means that even a small reduction in work function results in a very large increase in emitted current. This explains why materials with lower work functions such as LaB6 can produce significantly higher beam current at lower operating temperatures compared to tungsten. From an SEM operation standpoint, this relationship is critical. The electron source must supply adequate current while maintaining beam stability and reasonable emitter lifetime. Lower operating temperatures reduce thermal stress, improve stability, and extend emitter lifetime. The Richardson equation therefore connects emitter material properties directly to the beam current, stability, and practical SEM performance. For thermionic electron sources, it is always desirable to operate the electron gun at the lowest possible temperature. Lower operating temperature reducing evaporation of the filament, which directly improves source lifetime and stability. To achieve useful emission at lower temperatures, the material must have a low work function, meaning electrons can escape the surface more easily. Tungsten is commonly used because it satisfies this balance well. It has a relatively low work function and can produce a useful electron current at temperatures well below its melting point, making it mechanically stable and reliable. In practice, tungsten filaments operate at temperatures around 2700 Kelvin, where they produce cathode current densities on the order of a few amperes per square centimeter. This level of emission is sufficient for many SEM applications, especially where cost and robustness are important. However, the need for such high temperatures also explains the limitations of tungsten sources, particularly in emitter lifetime and ultimate beam performance. This motivates the use of alternative materials with even lower work functions, which we will discuss next. LaB6 sources follow the same thermionic emission principle as tungsten, but with an important materials advantage. The key difference is the lower work function of lanthanum hexaboride. Because electrons require less energy to escape from the surface, LaB6 filaments can operate at significantly lower temperatures than tungsten while still producing a strong electron emission. Operating at a lower temperature has several practical benefits. Filament evaporation is reduced, which directly increases source lifetime. At the same time, the emitted current density is higher than that of tungsten, meaning more usable electrons are available for imaging and analysis. In typical operation, LaB6 filaments run at around 1700 Kelvin compared to roughly 2700 Kelvin for tungsten. The work function is about 2.4 electron volts, almost half of that of tungsten, and this difference has a dramatic effect on emission efficiency. From the microscopist perspective, LaB6 sources offer a clear upgrade path from tungsten: improved stability, higher usable beam current, and longer filament life without changing the basic thermionic gun architecture. This makes LaB6 sources well suited for applications requiring better performance than tungsten while still avoiding the complexity of field emission guns. In thermionic electron sources, increasing the filament current raises the filament temperature, which in turn increases the number of electrons emitted. However, this increase does not continue indefinitely. The emission reaches a saturation point where further increases in filament current produce little or no additional usable beam current. Beyond this saturation regime, the extra heating mainly accelerates filament evaporation and structural degradation, rather than improving imaging performance. Operating in this region dramatically shortens filament lifetime without providing meaningful benefits. From a practical SEM standpoint, this means the electron gun should be operated just at or slightly below saturation. This ensures a stable beam current while maximizing filament lifetime and minimizing downtime and replacement costs. In routine SEM operation, this balance between signal strength and emitter longevity is a key consideration, especially for tungsten and LaB6 sources. So far in this lecture, we have focused mainly on thermionic electron sources where electrons are emitted by heating a filament. There is another important class of electron sources that operates very differently. In field emission sources, electrons are emitted by strong electric fields, not by high temperature. We will study the physics of field emission in more detail in the next lecture. For now, this slide provides a brief conceptual overview for completeness. In field emission, electrons are extracted from an extremely sharp tip, where the local electric field becomes very large. Because emission occurs from such a small region, the effective source size is very small, and the resulting electron beam is highly directional. These characteristics lead to very high brightness and excellent beam coherence. However, maintaining a stable clean emitter requires ultra-high vacuum, which is one of the key practical constraints of field emission sources. At this stage, it is enough to understand how field emission differs conceptually from thermionic emission. We will return to the detailed physics and implementation of field emission guns in the next lecture. This table summarizes the key differences between thermionic and field emission electron sources. Thermionic sources such as tungsten and LaB6 provide moderate brightness and a longer energy spread. Their beam stability is generally good, and they operate under moderate vacuum conditions. Because of their simpler design and lower vacuum requirements, they are less expensive and commonly used in conventional SEM systems. Field emission sources, in contrast, offer very high brightness and a very small energy spread, producing an extremely well-defined and stable electron beam. This enables higher resolution and improved signal quality, particularly at low accelerating voltages. These advantages come with practical trade-offs. Field emission sources require ultra-high vacuum, are more complex, and are significantly more expensive to operate and maintain. In practice, the choice between thermionic and field emission sources depends on the imaging requirements and constraints of the system, including resolution stability, cost, and operating environment. The key takeaway from this lecture is that the electron source is the most important component of an SEM because it ultimately sets the limit on beam quality and imaging performance. In this lecture, we examined the two major classes of electron emitters used in SEMs. We first focused on thermionic sources and saw how work function plays a central role in determining emission current and operating temperature. We then introduced field emission sources at a conceptual level and highlighted why they provide much higher brightness and better beam quality than thermionic emitters. In the next lecture, we will focus specifically on the physics of field emission, including the role of strong electric fields, quantum tunneling, and the different types of field emission guns used in modern SEMs.